started
Okay,
recording.
thank you.
Okay, thank you for reminding me. So is that working now?
Yeah, it's
Yeah.
recording.
Right. Okay, so let me go back and I'll try and just explain again what we were talking about. So just for people who are watching the recording and missed the first part of the conversation. So we were talking about shapes that we call platonic solids. These are solid three-dimensional shapes. And I gave an example of 5 shapes. And the 5 shapes are built up using simple pieces, using polygons. So you notice that this one here, this tetrahedron, this is built using triangles. The cube, this is built using squares. The octahedron here is built using triangles also. This one here, the dodecahedron, is built using pentagons. And here the icosahedron is built using triangles. Notice that the first one here has 4 faces, the cube has 6 faces, the octahedron has 8 faces, the dodecahedron 12 faces, and the icosahedron 20 faces. And you notice with each of these that only one polygon is used in each case. So the only thing we use here are triangles for this tetrahedron. The only thing we use here is cubes. The only thing we use here are triangles. You're not allowed to use, say, a square and a triangle, and say a pentagon. Okay, we can't use combinations of these things. I mean, there are lots of other shapes you can build doing that, but we're only interested in shapes that you can build using the same face, the same building block. So first of all, does that make sense?
Yeah.
Yeah. So you understand the rule here. This is like we're playing a game here. We're only allowed to use one type of face to build this. And there has to be symmetry in the sense that if you look at, for example, this icosahedron, look at this point. You have 1, 2, 3, 4, 5 triangles all meeting at this point. If you take any other point, take this point here, again, 1, 2, 3, 4, 5 triangles. You always have the same number of faces, okay, meeting at any particular point. There's a face, right? These are the faces. That's the face. So at any particular point, these are the vertices. That's a vertex. At any particular vertex, you have the same number of faces of the same type. Does that make sense?
Yeah, that makes sense.
Okay. So there are some rules here as to how we build these shapes. Okay. So it is a famous fact. It has been known for thousands of years that there are only 5 shapes you can build using this rule. They're called the platonic solids. And so the question we want to ask is, why is that so? How do we know that you cannot build another one? How, for example, do we know that you could not take hexagons like this and build a shape out of hexagons that satisfied all of these rules, where you had only hexagons and at each point you have the same number of hexagons meeting same angles and all of that? So the answer is you cannot. So no for hexagons. But why? How do we know that's true? Okay. And even if we only allow for triangles, for example, so we know we can build the tetrahedron from triangles, the octahedron from triangles, and the icosahedron from triangles. How do we know there is not some other shape, solid shape, that we can also build from triangles? Okay. So the answer is no. There are only 5, and these are the 5. But why? Okay. So before we go any further, do people understand the question?
Yeah.
Yeah, I'm not asking you to answer it yet. The answer will take a little bit of time. But do you understand the question, what the question is saying?
I understood it.
Yeah. Everyone else understand the question?
Yeah, we do.
You do. Great. Okay. All right. So let's try and answer this question. Now, so to answer this question, I want to say something. We will use a theorem, and I'm going to prove the theorem after we've answered the question. So a theorem due to Euler. Have you heard of Euler?
Yeah, he's famous.
Yeah, he was a Swiss mathematician. Leonard, his full name is Leonard Euler. From Switzerland. A couple of 100 years ago. So we will use, sorry, I forgot to say a theorem. I said it and I didn't write it down. A theorem due to Euler, okay? So what I'm going to do now is I'm going to tell you what Euler's theorem says without proving it yet. And then we will use the fact of Euler's theorem to answer the question about the Platonic solids, okay? And then when I'm finished, if we've time, I will prove Euler's theorem. If not, I'll prove Euler's theorem on another occasion. But let's at least answer this question about Platonic solids using Euler's theorem. I should say also that there are other ways of proving the fact about the Platonic solids that don't use Euler's theorem, much older methods. And we can talk about those as well at some point if you're interested. But I think the method using Euler's theorem is very nice. And Euler's theorem is one that's very useful for you to know for all sorts of reasons. So let me tell you about Euler's theorem. I mentioned it a bit last day. So we did a little bit of exercise. I'll just quickly remind you. We took some of these solids, for example, the cube. So here's a cube. Okay, can you all see my cube? Yeah?
Yeah, we see it.
Is it a nice cube?
Yeah, it's clear.
It's clear. It's a nice cube. Okay. So let's just notice that we have these things. These are vertices. That's a vertex. We have these parts. That's an edge. Okay. And we have these parts here. That's a face. You understand the different pieces? So the vertex is just a point. The edge is a line. And the face is something two-dimensional, like that. Make sense?
Yeah,
Okay.
that makes sense.
Yeah, we can do it for example, for the tetrahedron. Same thing. Okay. And if we were to count up the number of vertices, so this is the number of vertices, how many vertices would you count there?
For vertices.
4, yeah. If we do it for the cube, how many vertices? How many vertices on the cube?
8 vertices.
8, exactly. Okay, you get the idea? Okay, we can now look at the number of edges. How many edges on the cube? There's 1, 2, 3, 4 on the top, 1, 2, 3, 4 on the bottom, and then 1,
12.
2, 3, 4 on the side. So 12, right? Yeah. How many edges does the tetrahedron have?
Can you show me the shape?
There. There.
Here.
Here.
6.
Here. Here. Yeah, 6, exactly. And finally, count the faces. How many faces does the cube have?
6.
6. Okay, and how many faces does the tetrahedron have?
4.
4, yeah. Now, this idea of vertex, edge, and face, we don't just have to apply this to Platonic though. Right? So consider a non-Platonic solid. So let's try a square pyramid. This is like one of the pyramids in Egypt, right? Sorry, my
Yeah.
picture is very bad. Let me draw this better. I drew a bad picture. Okay. So now if we fill this in, we see the vertices. We have a vertex here, a vertex here, a vertex here, a vertex here, and a vertex here. If we look at edges, we have an edge here. Oh, sorry, we were using red for edges, weren't we? An edge here, an edge here, 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 and here. So tell me, how many vertices does this pyramid have?
5.
5, exactly. How many edges? Sorry, wrong color. Edges.
8.
8, yeah. And how many faces?
5.
5, exactly. Okay, so you get the idea. So you can take solids and you can break them up into vertices, edges, and faces, yeah, and count the numbers. Now, I made an observation last day. I'll just remind you of it here. In each of these examples, if you write down the formula V minus E plus F, so you take the number of vertices, you minus the number of edges, and you add the number of faces, you will get 8 minus 12 plus 6 in this case, which equals what's 8 minus 12 plus 6?
8 minus 12 plus 6 must equal 2.
Yeah, correct. In this case, 4 minus 6 plus 4 equals
6. Oh no, 2.
2. In this case, 5 minus 8 plus 5 equals
2.
2. Beginning to see a pattern here?
Yeah, it's all the result is always 2.
Yeah. So this is Euler's theorem. For solids. And I'll just say solids. I mean, I need to be a little bit more. If I was stating this really carefully, I would have to say more than just solid. I have to explain for which types of solids this is true. But for the purpose of this conversation, it's going to work in all of our cases. So Euler's theorem here for solids is that V minus E plus F is always equal to 2. Okay? You'll always get that. So does that make sense?
Yep.
Okay, so I haven't proved it yet. So proof later. We still have to prove Euler's theorem. I'll come back to that. So you just have to trust me right now. But I've given you some evidence, at least, that it looks like it's true. If you want to take a nice example, if you take a football, okay, many of you know that footballs often have a patchwork on them with
Yeah.
this kind of thing. Yeah, you've seen this, yeah, etc. So football made from hexagons and pentagons. Okay, and you can do this. So exercise for you, if you go find a football, count V, E, F, and check V minus E plus F equals 2. So in this particular case, you know, your vertices, here's the vertices, like this, and so on, and here are the faces, or here, the edges here, here, here. So you can do it yourselves, right? You can go ahead and actually, you might want to put like little stickers or markers on the bits that you've already counted. But if you go and check that formula, you'll see that it works. Okay.
Okay,
Or
sure.
if you're playing a football match and you get bored playing, or you get injured and you have to sit down, you can count those things. Okay. All right. Does that make sense as an exercise?
Yeah.
Great. Okay. So this is something we'll come back to. All right. Okay, so now let's consider the original problem, the 5 solids. So oh. Euler's theorem. So do you understand what I'm going? I'm not asking you to explain how I do it yet, but do you understand what we're doing, what my plan is to do? Yeah?
Yeah, we do.
Remember the original problem back up here. We want to show that exactly five of these ones. 1, 2, 3, 4, 5, and that there cannot be any more. Okay, so we're going to try and use Euler's theorem to do that. Okay, so let me go back down here. All right. Now we're going to do a little bit of algebra here. So, now, what I want to show is that x will have to be one of the 5 we've already seen. Right? But we don't know that yet. We can use that a tonic solid.
Are you talking, teacher? Because your voice is unclear.
Can you hear me now?
Now, now we can hear you.
Okay. All right, you hear me now? Yeah? Yeah. All right, so let's assume that we have some mystery Platonic solid X. And we want to then argue the case that it must be one of the 5 that I've described earlier. Well, let's consider some facts about X. So X has V vertices, E edges, and F faces, which satisfy Euler's formula, V minus E plus F equals 2. So this is Euler. Okay, so we're assuming this has to be true. We haven't proved Euler's theorem, but it's true, and I'll give you a proof of it next time. Is that fair?
Yeah, that's fair.
Great. Okay, good. Now, so let's leave that aside for a second. I need to introduce a couple more terms. So let S equal the number of edges on a face of X. Remember, to be a Platonic solid, all the faces have to be the same. They're either all squares or all triangles or something. So you can have, there's a single number S, which is the number of edges on a face. So for example, if X was the cube, what number would S be? So example,
for a cube.
Yeah. X is a cube. S would equal.
Um.
Well, let's draw a picture. Here's a cube.
12.
There's a cube. And what do the faces look like?
There are 6 faces.
Yeah, 6 faces. What do they look? What does each face look like? What kind of shape is a face?
Square.
Yeah, and how many edges does the square have?
4.
So the answer here is 4, right?
Yeah.
Okay. If X was equal to a tetrahedron, Okay, what would S equal?
3.
3, exactly. You understand what I mean by S?
Yeah.
Okay, so S for each solid X, there is a number S, which is the number of edges on a face. Okay. Okay, great. And then the second term I wanted to describe is let M equal number of faces which meet at a vertex that's a corner of X. So just to give you an example, let's go back to the cube. If you take any vertex like this, how many faces meet at that vertex?
3.
For a cube. Oh.
Yeah. There's three faces, yeah? 1, 2, 3. Yeah? So in the case of the cube, if X is the cube, S will be 3, yeah? Or sorry, M I should say would be 3. Yeah?
Yep.
Make sense?
Yeah, that makes sense.
Yeah. What if we had let's say doing of it, let's try an octahedron. So an octahedron, sorry. So we take a square base and we put one on top of the other like this, right? So if you look at this particular vertex, you have how many faces? 1, 2, 3, 4. So X is the octahedron. The octahedron, remember, is 2 square-based pyramids on top of each other. Then M would equal 4. Does that make sense?
Yeah, that makes sense.
Yeah? You can all see that? If you like, we can go back up and just look at the pictures of the solids from earlier. Here they are. We've kind of written on them a little bit, but I'll zoom in. Just erase here. Now, let me see if we can work out M for this guy. Sorry, I don't know what's happening. Sorry, my computer's doing something I don't want it to do. All right. So here's can you see my I'm using the highlighter here. This is my dodecahedron, yeah? Yeah. Okay. So if I take a vertex, is everyone with me? You can hear me? Hello?
Yeah, we can all hear you.
You're all here, right? So if I take a vertex like this,
Yeah.
so what would the number M be now? How many faces are meeting at that vertex?
3.
3, yeah. 1, 2, 3. Everyone see that? So M here would be 3.
Yeah.
Okay, so you understand these numbers S and M. What's S in this case?
5.
5, yeah, because 5 edges around a face. So S is 5. So in this case, M is 3, S is 5. Okay, I think you understand this, right? So for every single solid X, you have these numbers S and M. Okay, so each X has numbers S, comma M. Now, let's make some observations about this. You know what this is. S is the number of edges around a face, and this is the number of vertices that, her faces that meet at a vertex. So here's what we can say. Suppose I take the number of faces, F. So that's all of the faces. And each face has this number S edges around it. If I multiply S by F, Does this give me the total number of edges on the solid? Think about this for a second. Suppose I take the cube. Let's do this for the cube for a minute and see what happens. Okay. So remind me, what's S for the cube?
4.
4, right? So there's each face has 4 edges. So S is 4. And what's the number of faces on the cube?
6.
6, right? So in this case, this would be 4 times 6. And that would equal what?
24.
So is 24 the total number of edges on the cube?
Okay.
I'm asking you, is it? What's E for the cube? Count them.
E for cube.
Yeah. What's the number of edges for the cube?
12. So we divide
12,
it
right?
by 2.
So 24 is not correct. So what's going on here? How come our method didn't work? Why did multiplying face
Because of the
a face times the
intersection.
number of edges of the face not give us the total number of edges?
Because
Yeah,
of the
exactly.
intersection.
Intersection, exactly. So that's exactly right. This edge here, for example, is shared by 2 faces. So what's actually happening is here, what we're getting here is not the total number of edges, we're getting twice the total number of edges, because every edge appears on 2 faces. Okay? Each edge is on 2 faces. So we get what's called a double counting. Does that make sense? Do you see that?
Yeah.
Yeah.
Yeah, we see that.
Yeah, but you still get a nice formula though, right? You still get a nice formula. You get that S times F equals twice the number of edges, right? So we'll put a box around that. Does that make sense?
Yep.
Okay. Now, let's do something similar with the other one, okay? Now let's consider, so remember what M was. What was M? M was the number of faces that met at a particular vertex. So there's your vertex, and you have faces meeting at the vertex. There's the faces like that, and there's the vertex here, right? So M is the number of these faces. Does that make sense? So what's M for the cube?
Yeah, it does. 3.
Yeah, there's my vertex. 1, 2, 3 faces. Yeah, okay. So you understand what M is. Okay, so what if I multiply M, okay, by the number of faces? Sorry, not by the number of, I beg your pardon, not by the number of faces, sorry, by the number of vertices. I'm sorry, by the number of vertices. So there's a vertex, and each vertex I get a collection of faces. Does this give me the total number of faces overall on the cube, or on the shape? Well, just do an example. Let's again do it for the cube, right? Here's the cube. All right, here's the cube. Okay. So what's M for the cube?
3.
So that's 3. And what's the number of vertices for the cube?
8.
8 vertices, which equals 24. So that's not the number of faces, is it?
No, it's not.
No, it's not the total. The total number of faces is only 6. It's actually giving you too many, 4 times the number of faces. Okay. So what do you think? Can we get any sort of nice formula here? Well, here's the funny thing, right? You notice that S, what was S? What was S for the cube?
4.
4, yeah. And we have 4 times too many faces here. This is 4 times the number of faces.
Yeah.
But it's actually equal to S times F.
Times F.
Yeah. So what we actually get in general is that mv equals s times f. You'll always get that. And that in turn is equal to 2e.
E.
So actually we get an even better formula. I'm only showing you the example of the cube, but this is true more generally. Does that make sense?
Yeah, that makes sense.
Okay, so let's summarize.
Is there
We have
is there
two-
a proof for that?
There is, and that's an exercise for you guys. So I'm not going to prove everything because it'll just take too long, but I'll let you guys try and prove that.
Okay.
Okay. I mean, I think you can see how it works in the case of the cube. So, but I'll let you prove
Yeah.
that.
Okay.
Is that okay? I'm going to
Yeah,
give you
yeah.
some little exercises to prove because I'll run out of time otherwise. So I'll let you guys prove that. But now let's consider we have these two formulae that we've established. Two formulas. The first one is the Euler formula, V minus E plus F equals 2. And the second one is MV equals SF equals 2E. So these are the two formulae. And I claim from these two formulae, we can actually show that there are exactly only 5 possible platonic solids. So the question now is how we do that. But do you at least understand what I'm saying, even if you don't believe me yet? Yeah? Are you happy?
So far, so good.
So far, so good. Please just tell me if you're not happy or if there's anything confusing. Sorry, I'm changing my seat here because I'm a bit sore. I've been sitting in the same place for too long. Okay, so let's do this. So what we want to do is combine the two formulae, right? So we have, if we go, well, let me color code this. So if we take the MV here and the V here, so we have MV equals 2E, all right? So that means V equals 2E divided by M. And then I'll use a different color for F. So we now have SF equals 2E, right? So SF equals 2E, and that means that F equals 2E divided by S. Does that make sense?
Yeah, yeah.
And so we can then take the first formula. Let's call this formula 1 here, formula 2. So now 1 becomes, so the V becomes 2E over M minus E, and the F becomes 2E over S. All of that equals 2. So we get a single formula which looks like that. You guys happy with that?
Yeah.
Okay. We can tidy this up a little bit. Okay. Remember, E, the number of edges, is always a positive number, so we can divide across by E. So this is the same as saying 2 over M minus 1 plus 2 over S equals 2 divided by E. E is positive, so you can do that. And then I can rearrange a little bit further. We can divide across by 2. This is 1 over M plus 1 over S. I'm going to bring this guy over to the other side. Okay, so this is going to equal, sorry, wrong color. It's going to equal 1 plus, sorry, 1/2 plus 1 over E. Everyone agree with that?
Yeah, I think that.
Did I do it correctly?
Wait, it must be correct, I think. Oh, yep.
I'll wait till you guys are happy.
Yeah, okay.
You're all
Wait.
happy?
Oh, yep.
Okay. So here's what we know. M, S, and E are positive integers. You all agree with that? E is the number of edges. S is the number of edges around a face. And M is the number of faces meeting at a vertex. So these are all positive integers. They can't be fractions or irrational numbers or anything like that. They're just positive integers, yes? They also cannot be negative. Do you agree with that?
Yeah, sure.
Here's what we also know. Right? We know that that S has to be bigger than or equal to 3. Yeah? Because S is the number of edges around a face, and the smallest face would be the triangle. Yes?
Yeah.
Okay. So if we start with that, okay, we can sort of rearrange this to try and get an expression for E. Okay, and essentially what we can do is we can sort of work our way through and try to figure out what's going on. So 1 over E is a positive amount. Yes? Do everyone agree with that?
Oh,
Yeah.
yep. That's true.
So now we get an inequality. So now we get 1 over M plus 1 over S has to be strictly, so to equal a half plus 1 over E, this has to be strictly bigger than 1/2. Do everyone agree with that?
Yeah, sure. Yeah.
Okay. And once you have that, you can start to make a table. Okay. So you can start with saying, okay, so try S equal to 3. Okay. Try S equal to 3. So that means 1 over S is 1/3. Okay. And that means that 1 over M, okay, has to be bigger than 1/2 minus 1/3, right?
Yeah.
Yeah. And so that means that 1 over M has to be bigger than 1 over 6. Yes? Everyone agree?
Yeah.
Yeah? Which means M has to be less than 6. Of course, M has to be bigger than 0. So those are the only possibilities for M if S is 3. Yeah? And you try those possibilities out. Okay? So you work your way down and you check. So then you check the possibilities. S equals 3. And you can try, for example, if S equals 3, you can try M equals 3. Okay, so that means you've got 1 over 3 plus 1 over 3 bigger than 1/2. Okay, like that. So that's a possibility. Okay, and that's the case when S is 3. You've got three edges around a triangle, and you've got 3 triangles meeting, and you can see what E would have to be. So what would E have to be in this case? So what would E have to be here? Well, then 1 over E would have to be 2/3 minus 1/2, right? So that means 1 over E would have to be what? 1 over 6, right?
Yep,
So
that's right.
equals.
Everyone agree with that? And so E equals 6.
Yeah.
So now you have the example where this is 3, and this is 6. What shape is that? Six edges built out of triangles. If S is 3, this means built out of triangles with 6 edges. What shape is that? It's the tetrahedron,
Wait.
isn't it?
Yeah.
Okay, you can see yourselves. Hang on. Okay, that's the tetrahedron. You can see the 6 edges. You see at each vertex you get m equals 3. Okay, at each face you got 1, 2, 3. So that's s equals 3, and you can count yourselves that e equals 3. It's the only possibility, right? So that was the first check, right? That was the first check where we did these two. Okay, so we're still checking s equals 3. So you have to go through all of the possibilities. If s equals 3, can m equal, what if m equals 4? Okay, so what happens when s equals 3 and m equals 4? So now we have 1 over 3 plus 1 over 4 equals 1/2 plus 1 over e, right? And you try to solve this, yeah? Right. Is this making sense?
Yeah.
Yeah, you understand we're still on s equals 3. We're trying all the possibilities. Right, when s equals 3, go back up, you know that m is constrained. You know that m is in here. So I'm trying the numbers in here. Okay. So m, sorry, I don't know why I wrote a 0 here. This is to be 3, sorry. M is at least 3. Sorry, no. M is at least 3. Okay. So we try m equals 4. And so now rearranging this, what does 1 over e have to be? So 1 over e has to be 1 over 3 plus 1 over 4 minus 1 over 2. Okay, so 1 over 3 plus 1 over 4. Let's do all of this in twelfths. This is 4 twelfths plus 3 twelfths is 7 twelfths minus 6 twelfths. Sorry, minus 6 twelfths, which equals 1 over 12. So what is e?
Wait. 1 over 12.
Yeah, so e would have to be 12, right? Okay, so does this work? Can you have such a shape? So s equals 3 means it's made of triangles. Okay, so can m be 4? Yeah, so that's 4 of them meeting. So it means you have 4 triangles meeting at a point. Okay, so this is triangles. Make it better. This is made out of triangles. 4 triangles meeting at a point. So at each particular point, you have 4 triangles meeting. That's what it looks like at a point. And you have 12 edges. So m equals 4, s equals 3, and e equals 12. Anyone want to tell me what shape that is? Do you want to go back to the top and we'll have a look? Go back up to the top, you can look at all the shapes, and you guys tell me which one that is. Remember, we're looking for s equals 3, m equals 4, e equals 12. Which one is that?
Wait. S equals 3.
Well, how many shapes have
the
12 edges?
Just one.
You sure it's
The
just
cube
one?
one.
The cube
Oh,
has
wait.
12 edges, but the cube doesn't have the
And
triangular faces.
Yep, octahedron.
Octahedron, exactly. That has 12 edges, it has triangular faces, and each vertex has 4 faces meeting. So this one is the octahedron. Make sense?
Yeah, that makes sense.
Okay, so I'll just go back down. So look, I'm not going to do all of them. I'll just tell you what you have to go through step by step. Hang on, sorry, size. You can see how this works. Sorry. Lost it. Here it is. I think the laptop is short on memory. So idea. So this is, by the way, the octahedron. Create a table. So we know that S has to be at least 3. M has to be at least 3. Okay. We also know that 1 over S plus 1 over M must equal 1 over 2 plus 1 over E. And that means that in particular, 1 over S plus 1 over M. Oh, sorry, my pen just ran out of ink, so just give me a second. That means that 1 over S plus 1 over M has to be smaller than. So using all of those constraints, we have to put together all of the possibilities. 1 over S plus 1 over M has to be bigger than, not less, bigger than 1/2. Okay, it has to be bigger than 1/2. All right. Does that make sense? And so if you start with S
your
equals,
your voice wasn't clear. Can you repeat what did you say?
okay, is it back? Is it back? Is my voice back?
Now, yeah.
Yes. So for example, if you tried S equal to 2, S equal to 2 is not possible because 1 over 2 plus 1 over M here. So S equal to 2. So this is 1/2. Sorry, what am I saying? Sorry, S equal to 2 is not possible because S has to be bigger than or equal to 3. I'm sorry. So S has to be bigger than or equal to 3. So if you try S equal to 3, as I said, you get 2 possibilities. So S equal to 3 and M equal to 3. This gives you the tetrahedron. So this is the one that forces E equal to 6. And then if you try S equal to 3 and M equal to 4, this gives you the octahedron. And this is the one that E equals 12. Okay, that's what we did so far. But now let's try S equal to 3 and M equal to 5. Sorry, my pen keeps running out. Just give me a moment. I'm almost finished. I'm just going to do one more and then we'll stop. Is this making sense, this table? Hello? Hello?
Yeah, I can. Yeah. Wait.
Yeah. Okay, so now let's try M equal to, what would be next to try? M equal to 5, yeah? So let's try M equal to 5. Okay, so what would happen now? Well, if M is equal to 5, that means we have 1 over 3 plus 1 over 5 equals 1 over 2 plus 1 over E. Okay, so 1 over 3, 1 over, so we need to put everything here in what fraction? In, I guess, in 30ths. So this is 10 over 30 plus 6 over 30 equals 15 over 30 plus 1 over E. Well, now we have 16 30ths equals 15 30. So we now have 16 over 30 equals 15 over 30 plus 1 over E. So what must E be in this case?
30.
E would have to be 30, yeah. Okay. So what are we dealing with now? We're dealing with, again, triangles. We're still dealing with triangles. That's triangles. Okay, and we're dealing with 5 triangles meeting at a point. Any idea what shape that might correspond to? Let me go back up and I'll show you the shapes again. So here's the shapes. Maybe I'll get out the eraser for a second. So if you look at this one here, you can see sorry, it's not letting me. No, there we go. You can see the vertices there. There's a vertex there. How many faces are meeting at any vertex? How many faces are meeting at this vertex here? 1, 2, 3, 4, 5. So can you see in this particular case, m equals 5, yeah? Does that make sense? What's s in this case?
3.
3, because we're dealing with triangles, yeah? And you can go ahead and work out yourselves. You can count them if you like, that E in this particular case is 30. But you can see it yourselves in the formula. Remember that, remember that S times the number of faces equals twice the number of edges, for example. So this has 20 faces, so this would be 3 times 20 equals 2E, so E equals 30. But anyway, you can see that yourself. Does that make sense? So this one is the icosahedron. All right, it takes ages to go back down. Got this giant blackboard. So this is the icosahedron. And so the very last one I'll do is what happens if you say S equals 3 and M is bigger than or equal to 6? Because we've done M equal to 3, 4, and 5. What if I chose 6 or bigger? And you see what happens now? I get 1 over
There's going to be a negative
3, yeah, plus 1 over M equals 1 over 2 plus 1 over E. So that means then if you rearrange these things, so this left-hand side here, you're going to have 1 over 3 plus, let's say 1 over 6 or bigger than or equal to 6. This side here is going to be less than 1/2. Does that make sense? So this side here is going to be less than 1/2. But the right-hand side is bigger than 1/2. So that means these cannot be equal. Does that make sense?
Yeah.
Yeah. So that's why you can't go any further than 5. So if S is 3, you're only allowed to have M equal to 3, 4, or 5, and that's it. And the next one to try is S equals 4. And then you'll find it'll work for M equals 3. Okay, you can make that one work. And I'll leave it as an exercise for you to work out which shape that is. Okay. And you'll find that's the only one that works there.
Sure.
Does that make sense?
Yeah.
Just playing around with these kind of inequalities, you'll find this is the only one that works. And then there's one more possibility, which is S equals 5. Okay. Okay. If S equals 5, you'll find only, I'll let you guys work out M, but you'll find that only one works. Only one example. And then for the reasons I've given you, S, oh, sorry, pen has just run out again. But for the reasons I've given you, S cannot be bigger than 6. It cannot be bigger than 5. It cannot be 6 or bigger for exactly the same reason I just gave you for M. Okay. So S cannot be bigger than 6. So 5 possibilities, that's what you find, 5 possibilities. S equals 3, M equals 3, S equals, 3, M equals 4, S equals 3, M equals 5, S equals 4, it turns out that M equals 3 is the one that works here, and S equals 5, and it turns out M equals 3 is the one that works here. And you cannot go, so S comma M have to be between 5 and 3. And so that's it. 5 possibilities. 1, 2, 3, 4, 5. Okay, and I'll let you guys fill in the table. Does that make sense?
Yeah.
I know it's a lot to take in, a lot of detail, but I think if you read through it and sort of put it together, and there are little gaps that I didn't do, little exercises in there that you can fill in yourselves. Okay. Can you see, I'm about to stop. Can you see how important Euler's theorem is in this?
Yeah, sure.
Yeah. Okay, so what I might do next time then is to explain to you why Euler's theorem is true.
Okay.
I'll give you a very nice geometric proof of Euler's theorem. All right, I'm going to stop sharing the screen for a second, just so I can see you. Hold on a minute now. Stop sharing the screen. You guys still there?
Yeah.
Hello? Everyone okay?
Yeah, we can hear you.
Yeah, great. Okay, was that helpful? Was that useful?
Yeah, sure. I think we learned a lot.
Good. Okay, you're very polite to me.
No, actually, I think it's very nice. It's very exciting to learn math this way.
Great. Okay, I'm happy to hear that. Well, look, you've got plenty to think about, and we'll continue the story next week. How are your friends doing? I know that not everybody's here today. Is everybody doing okay?
I think they are. We didn't connect with people from Gaza. I think they do not have internet. There is a lack of internet, so you do not actually contact them that much.
Yeah. Have you heard any news from them?
Maybe Muhammad knows.
Yeah. Hassan is good, but not that good. He said the internet is very hard to get.
Yeah.
So so our friends from Gaza can't join us, sadly.
Okay. Are they able to see the recording? Maybe.
No, they can't.
Nothing.
They can't use internet
at all. Okay. Well, maybe at some point in the future they can see the recording.
Maybe after 15th of the next month.
Yeah. Okay. Well, I wish them my best, and if you're talking to any of them, tell them that everybody in Ireland is thinking about them. So
thank you so much for asking.
Very sad to hear of what's going on. And how is it? Who is it? You said Hassan. Is that who's in Gaza?
Hassan is in Gaza, and he can't use internet. That was what I said.
Yeah. Hassan. Okay. And do you know anything about where he is now or his family?
He didn't tell me, but he said that they are not at home from the beginning of this month, I think.
Are they in Rafah?
I think, yeah.
All right. Okay. Well, look, please send my best wishes to anyone there. And as I said, we in Ireland, we talk about Palestine every day, and we care very much.
Thank you, guys. We are so thankful for you.
We have finally persuaded our government to fly the Palestinian flag in our city government buildings. So
that's nice.
Yeah, so things are changing here. I mean, most Irish people are very sympathetic to Palestine, but it's a struggle everywhere. But I think in the end, we are winning slowly. I know it doesn't seem like that for you guys, but around the world, I can tell you that Palestine is everywhere. People are talking about Palestine everywhere.
Yeah, we heard that a lot from our friends, like outside of the country. And we are so grateful for that, and we appreciate it. We appreciate every help that you guys can do, and
Well, even in America, I was in America a few months ago, and there were people in America flying Palestine flags. Like lots of ordinary people in America are on your side. They care about Palestine, and
we've seen like Ivy League universities and top universities. Committees, they are trying to help Palestine, and
so it's the world is complicated, but there are lots of people in America who do not agree with the American government and are very supportive of you guys. So anyway, gives us hope.
Of course, yeah, it does.
Yeah. Okay, well, listen, it was great to see you guys, and I'm happy to talk again next week if you want to hear more about Euler's theorem.
Yeah,
So,
sure.
and until then, have a safe week. I hope you guys are all right.
Thank you so much. See you next Saturday.
No worries. See you. Bye.
Bye.